But really, do you need a review on recursion? Yes? No? Maybe so? I'm not insulting you, right? Something you learned, you being the expert at already. I have to repeat that with you. I bored you? No? Yes? Okay. We do a review. A little bit, okay? Okay, a review. I need... oh, here we go. That's what I need. Review. All right. Here is a little review of recursion. Okay, so you know the concept already. And, well, as a checkpoint, what do we need? What is the main component when you want to write a recursive program? Say again? Starting point, there's a terminology. Can we speak about your starting point in the terminology? Are you looking for a starting point or the termination point? Please try to remember these terminologies, okay? Because it's used pretty commonly, and when we speaking of recursion, this terminology will tend to pop up a lot, and so you would be expected to know what we are talking about. Okay? So a normal structure for a recursive program or a recursive method would involve some kind of an if-else statement. And in the if-else statement, okay, part of that if-else statement will involve a call to itself, right? That is why it is called recursion in the first place. The program is recursive because it involves a call to itself. So within that if-else statement, it involves a call to itself. And that part of the if-else statement that involves a call to itself, we call it a recursive part, okay, or the recursive case of your if-else statement of your recursive program. All right. So we have an if and else. So basically, a very simple one would involve just two cases. All right. That is very simple. It could be more than two cases. All right. We from time to time run into the recursive problem that involve 3-4 cases. But the simple one tend to involve about 2 cases. One case, okay, will be the part where you put the recursive case into it or recursion into it. That recursive case involves a call to itself, right? And now, when a program calls itself, what would be the concern you have to worry about? When a method calls itself, what would be the issue or the concern that you have to worry about? Say again. Why index of a bound? Be more straightforward, be more simple. Don't go overly too complex. You're speaking of index upper bound that is only applicable to an array. We're not talking about array. Be more generic. I know you know the answer. Answer it right. Knowing and answering, different thing, right? You know what the answer is in your head. Be sure you can communicate it out too. Based on your answer, I know you know what the answer is. You just need to communicate it. What is the concern when a method in the recursive part of your if-else statement, okay, this recursive part, the method calls itself, then what do you have to worry about? Say again. Is it? You said the anchor? You actually use that terminology? Anchor like ANCHOR? That is the second part. The base case or the anchor part or the anchor statement, of course, that's the anchor. No, it's something you have to worry about. That's the next step. Okay, now we worry about the first step first. When a method calls itself, before you worry about the anchor, because the anchor will be your answer to this worry. Okay? Oh, part of the answer anyway. When a method calls itself, the thing that you have to worry about is how to make sure that the method would not call itself infinitely, forever. Right? Because you have A and then A call A. Of course, if A can call A, it will call A and 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 call A. If you don't have any mechanisms to stop it, it will call itself forever. Okay? So in the recursive part, what you have to take care of in order to make it work is to be sure that when a method calls itself, it must be in a degenerative form where somehow it has to decrease the step of the parameter, say, that you pass into the method until it go and converge. You can use converge. It converges into the anchor, okay? Or in this case, I'm going to say the base case. If you cannot make sure that the recursive call converges to the base case, your recursive method will blow. Okay, it will not stop. It will go on and on and on and on and on forever. So in any recursive method, there's two very important parts, normally stipulated by the if-else statement. The first part involves the recursive call. And this recursive call, you have to take care to make sure that it will eventually converge to the base case or one of the base cases. It could be more than one base case. Okay? And then there is another part of the if-else statement that deals with the base case or the anchor case that you just mentioned. This base case is a case where you use it as the termination point. If your recursive call can converge to the base case, then the base case can guarantee the termination. Your recursion will eventually stop. And that is the whole concept of recursion. Easy, right? When you study recursion, what example did you use? Say again? Factorial. Okay, let's do another factorial. All right, so we have factorial. We started out with mathematical definition of factorial. We have factorial of 0 equals to 1, and we have factorial of n. Of course, based on the mathematical definition, is n multiplied by factorial of n minus 1. So basically, an n factorial can be defined recursively, okay? N factorial can be defined recursively as n multiplied by n minus 1 factorial. Okay? Now, I want you to work as a group again. Okay, so spread out, form the group. I want you to work on the base case, the recursive case, and then when done, I want you to come up and I'm going to use the Dr. Java's, this solution will be short. Just type it out. Okay, I'm just going to randomly pick one of the groups. Okay, spread out. You can use all the flipboards over there. You don't have to be so close to the screen because, well, I'm going to go through these slides. So I want to make sure that you can see them too. Since you work on this already, so I would expect the solution to come easy for you guys. Okay, so I'm going to give you about 10 minutes. This is a refresher, all right, a review of what you learned already. We're going to move on to several other problems. So based on this definition, I want you to identify the base case, the recursive case, and then think about the code, what the code should look like. Find a group. Do not stay alone. It is easy, right? I heard activity, so you're almost done. So folks, what is the best case? What is the best case? The anchor 0, what? Okay, 0 is the base case. So it will look something like what? If this is 0, you return 1. Okay, so that's the base case. Recursive case. Well, you have the definition here already. So if it's not 0, so that's an else. Okay, if it is not 0, you return what? N, and then factorial of n minus 1. Right? So that should be easy. So you want to come out and show what it's like? No, that's good. Just Control S. Stop. Okay, Control S. Okay. With what you have here, can you demonstrate whether or not it is correct? Can you test it? Do not use main because don't waste time on main. Can you just test this? How? No. Just go to interaction pane. Control S first. I guess you have to compile first. Okay, so you compile, everything is good. Just raise the bar up a little bit. You want the area, just touch it and move it up. Yeah, okay. How about 10? Yeah. No, it's not. So you haven't used interaction pane that much. Don't touch that. Just work on the interaction pane. Anyone know how to use the interaction pane to test whether or not this is correct? Anyone knows? If you know, just please come out, okay? Okay, your friend is here. You got to be careful why it doesn't work. Now try to find the answer for yourself. It is a good review. Why just typing in factorial 10, it doesn't work? Why couldn't you see it? Just remove the semicolon. Retype it, remove semicolon. When you use semicolon, it treats it as the whole statement and it hides the information. So remove it now. And this is correct. I checked before. But that's the beauty of using the interaction pane. Now, why just when you use factorial 10, it didn't work. Why is that? Because factorial is the method, it needs to identify where you can find the method. Okay? In this case, there are two approaches in identifying the place where you can get the method. One, you use the object. The other, you use the class. In this case, are you supposed to use the object or the class? Class, why? Why class? Because, I'm sorry? Yes, because it is a static method, that's why I use class. Now, same thing here. If I remove static from here, I compile, it will compile. Okay? But now when you try to do the same thing, recursion, dot factorial, and then you say 10, right? It will not work anymore because it's no longer a static method. So in this case, how will you test? What you're going to need to do? Just factorial? And no, it doesn't work. Yes? No, we don't want to write a main method. Sorry? Just stand what? No, you use new. Okay? Or more familiar, it will look something like this. When you actually write the code, especially if you are going to plan to write the main method. Okay, it will look something like equals new recursion, right? And then you do R factorial 10. That is the reason why I put static in there, because I don't want to create the object. You're supposed to know all this by now, okay? Okay, so we're good, right? Put a static back in because I like it better in this case. Now, where were we? So let us go through this one more time as a review for those of you who's trying to cope with the concept too. Okay, so we are going to work this out step by step. Hopefully you can get an insight out of this. The example will start with factorial 3. Okay, the way it goes with recursion is that if you start out with factorial 3 and we know that the recursive part would go like 3 multiplied by factorial 2, right? So that's going to happen because that is the definition of it. Factorial 3 equals 3 multiplied by factorial 2. 3, the value is known. That part, the value is not known. Not yet anyway, right? So we are going to work on that part. And we know by the definition, factorial 2 is what? It is equals to 2 multiplied by factorial 1. Okay, so we're going to do that. So that becomes 3 multiplied by that part, 2 multiplied by factorial 1. Factorial 1, do we know the value yet? No, we don't. So we know that it is equal to 1 multiplied by factorial 0. So we're going to do that. So you have 1 multiplied by factorial 0. And now factorial 0 based on the definition we saw earlier, we know that the value is 1. So you're going to get that part. Now, since you got to this part using the expansion of the definition, okay? Remember in mathematics, when you see the parentheses, you are supposed to work out the value in the parentheses first, right? So that meant, which one will get evaluated first? This part. 1 multiplied by 1 right here. So this is interesting. This is how recursion actually works too. You started out with factorial 3, but the first evaluation takes place where? Right here. Factorial 0, where you get 1 multiplied by 1. Okay? So you go out from 3 to 2, 2 to 1, 1 to 0, and then you start evaluating from inside out. Okay? You go from outside in. You started out from 3, and then you go inside 3 to 2, 2 to 1, 1 to 0 based on the definition. And once you get to 0, you evaluate it from inside out. You expand or you recursive. You do the recursion from outside in. You evaluate from inside out. So this will get evaluated first. And so you have 1 as a result. And so you have 2 multiplied by 1. And then this is the next parenthesis. So you get 2 as a result. You have 3 multiplied by 2. And then eventually you evaluate the outermost parenthesis, which is 3 multiplied by 2, and the result is 6. Okay, that's how the recursion actually works. It expands recursively from outside in until you get to the last one, which is your base case. Okay, once you get to the base case, you don't expand any further. You stop. That's why it is the base case. All right. Once you get to the base case and you stop, now you start evaluating, and the evaluation will go in the reverse direction because you go from top to bottom. The evaluation will go from bottom to top. All right. You go from outside in. You evaluate inside out. That one will be pretty critical in your understanding of how recursion works for some of the problem. We'll see very soon because we're going to work on some of the problem there. All right. So that's the factorial. I am just going to go through this quickly because we saw that already. All right. This is what we call the stack trace. Okay. Did you work on the stack trace too in either OS or data structure? Either one of them. Yeah, so I'm going to go through this. Okay. I assume that you know this already. All right. Now, what is this? Anyone still remember this? Yes, it's Fibonacci. Okay, so Fibonacci. And here's the definition of the Fibonacci. All right. When f is 0, the Fibonacci number returns 0. Otherwise, a Fibonacci returns a value of n plus fn minus 1. Is that right? It's kind of weird for me. Yes. No, it's not. It's that's the first two one. All right. Here's the more complete definition of it. All right. So the Fibonacci, you have fib right here. 0 returns 0. Fib 1 return 1. And then the Fibonacci of n, it will return Fibonacci of n minus 1 plus n minus 2. Okay, that's more like it. And this only works if the index of n right here is greater than or equals to 2. Right? So this is the mathematical definition of the Fibonacci. And Fibonacci is a very wonderful, miraculous number. It's quite a miracle series that If you have time to study it, you will be amazed. It's quite amazing. Okay, a lot of patterns in nature could be matched into or could be described using the Fibonacci sequence. Kind of interesting. Okay, some of the interesting stuff. Say, for example, if you have a pair of rabbits, for example, okay, put into the stable, okay, and you allow them to breed and work out their relationship, the number of the rabbits in that stable will grow based on this Fibonacci series. It's kind of interesting. Okay, now let's talk about this. How can you solve the Fibonacci numbers using the recursive approach? Okay, talk among your groups. You have the definition, so this should be very good and easy. Talk among your group. I'll give you about 5 minutes. So if you want to do recursive method call to compute the Fibonacci number, what would you do? What would be your best case, or what would be your best cases? Okay, and what about the recursive case? What the code will look like? Yes, some of you will come out and try to work on the code again. Just give you a little hint. Solving this Fibonacci series here recursively is not the highlight of this particular example. The highlight will be the trace. We're going to look at the steps in the calculation, how things go recursively in solving Fibonacci series or this Fibonacci problem. So we're not doing the series, okay? We want to say, if we say fifth 10, what's the value that come out of fifth 10? Okay? So that's what you want to solve. So, what's the best case? Well, predictably, the best case are as defined here. These are the two best cases you will need, right? So you have two best cases, not just one, but two. Agree? And then, based on the definition too, that would be your recursive part. Do you agree on this? Right? So, who want to come up and write the code for this one? Okay, please. I started for you that much already, so you finished the rest. No, you need the parentheses. It's not going to work. It's not the full, not full class header yet, and the method header yet. Okay, save, compile, and test. Try what, 10? I know, 15, what is it? Is that correct? Okay, congratulations, thanks. Okay, well, that one was nice. I like that one. Okay, so you merge the two base cases together using the OR and then just return the value of n because that corresponds to the base case value already. Okay, and the rest is just to return the recursive part of it. It's fifth n minus 1 plus fifth n minus 2. The more interesting aspect of this particular example is not the code itself, because by now you probably can see if you can write the mathematical definition in recursive form, it becomes so easy to change that or convert that into the Java form. Okay? What is more interesting in this case is when you try to trace the operation, how it proceeds in order to do the calculation. You see that it's quite interesting. Okay, here we go. And here's how things go with the FIB4. Okay, FIB4. Now, when you start working out on FIB4, okay, a call to FIB4 will result in what? Will result in a call to the recursive part that expand FIB4 into FIB3 plus FIB2, right? So you have FIB3 right here plus FIB2 right here. And since normally in the typical Java statement, the evaluation actually goes from left to right, okay? You will run into FIB3 first before you're running into FIB2. So that will be expanded first from FIB3 to FIB2 plus FIB1. Okay? So you started out with 0, a call to FIB4. And then at 1, a call to FIB3. And note, this one is number 11. Okay? So you're going to go all the way to the left first. You run into FIB3. Okay? That's the next call to FIB3. And once you make a call to FIB3, you expand it out to FIB2 and FIB1, right? So you have FIB2 and FIB1 right here. So from 1 to 2 right here. 2 is a call to FIB2. All right? And with FIB2, since you see this one first, you're going to expand it up to 1 and 0. So you're going to make number 3 right here call to FIB1, and that you return 1. Okay? And then since that's number 3, that's number 4, a return of FIB1 is 1, so that one will be evaluated. Okay? At step number 4. Right, this will be evaluated at step number 4. A value 1 will replace FIB1. FIB0 will be next. That's why you have step number 5. A call to FIB0, it will be evaluated and it will return 0. So that's number 6. Okay? So at number 6, this has a value of 0. So now, by step number 6, you know that is 1, that is 0. So you can add it up. Step number 7, you return 1 of FIB2. Okay, so FIB2 is the value of 1 is returned right here. That is step 7. Okay, so 2 is known at step 7. So now you're ready to evaluate that, and that is step number 8. Okay, a return of value of 1 here is at step number 9. So by step number 9, you are ready to add these two up. Okay, so you return FIB3 at step number 10. So this FIB3 is evaluated, the value is known at step number 10. That is why you will come to FIB2 at step number 11. Okay, so you do the expansion first. Okay, you expand it from top to bottom. You do the evaluation from bottom to top. And you actually do from left to right. So this has to be evaluated first before you move on to that one. Okay, and you start working on the evaluation of this one at step number 11. By that time, the value of FIB3 is known. At step number 11, you work on FIB2, do the expansion of FIB2 to be FIB1 plus FIB0. That's 11, that should be 12. A call to FIB1. Okay, a return value will be 13. Then will be 14 right here. A call to FIB1, a return will be 15. Okay, so after 15 step, you are ready to return FIB2. So after 16 step, you can evaluate this at step number 17. So this is fun because now you have two recursive calls going on at the same time based on the Fibonacci series. And it is interesting to see that with these two Fibonacci recursive Fibonacci calls, you actually work on one before you work on the other. Okay? You work on one to the completeness, about 10 steps to work on this one before you move on to the next evaluation. Take about 6 steps to get this done and then add them up to return the final result at about step number 17. Okay, and that's the nature of recursion. You recurse and then evaluate. But you're going to have to recurse until you hit the base case. Once you hit the base case, you start to coming back up. Okay, on the way back up, you evaluate. Until you cannot do it any longer. That's your result. But if you have more than one to go, you have to do that first result, second result, add it up to get the final result. That's fun, right? Let's try this one. So this is a little summary of what we already discussed, the characteristic of the recursion. Okay? Our recursive methods have the following characteristics. One or more base cases. The simplest case, you try to do as simple as you can. Okay? These base cases are used to stop the recursion. And then every recursive call reduces the original problem, bringing it increasingly closer and closer and closer to the base case until it becomes that case. By the time it becomes that case, you stop, because when you say the base case, it returns some known value. Okay? And when it stops, you are now thread back, okay, along the recursion trace to go back to where the original point where you come from. Okay? So let's try this. Another example on problem solving. Let's assume that you want to print a message n times. Okay, you have a message, say maybe I love programming. Okay, so you want to print this message, I love programming, 100 times or 10 times. Can you write a program to do this recursively? Now talk among yourself. Okay, so you want to print a message. I love programming. I want to get an A. Okay, you want to do this n times. How can you do this recursively? To do this iteratively, it is easy, right? You just do, let's say n times for I equals 0, I less than n, I plus plus. System another print line. I love programming. I want to get an A. That's n times, iteratively. Okay, so iteration is no challenge. It will be an insult to your intelligence. So we are going to do what? Doing the same 100 or n times printing of the same message, but recursively. Try it. Talk among yourself. Don't forget the characteristic of recursion, a base case and a recursive case. And you'll find out that to do this effectively, what you need is what we call the recursive thinking scheme. Okay, you have to use your brain to think recursively a little bit, not iteratively. This thing, if you want to do using the loop, easy, okay? But recursively, a bit of challenge. So you all got the solution? Everyone? So what's the best case in this case? Did you get n equal to 0 because that's when you want to stop? So you want to print n times when n is 0, that is when you want to stop, or you can go the other way around, and when n is equals to that number, okay, you want to stop. That should be your best case. Either way, it could go up, it could go down, okay, depending on how you want to do n plus 1 or n minus 1. Okay? And the recursive case, all it does is just print. Okay, all it does is just print. Okay, so that sounds easy and straightforward enough. How about the code? Does the code actually as easy as we just described? Anyone would like to come up and show you what the code looks like? Anyone? Okay, we want to volunteer the code for this problem. What does it look like? Come on, folks. It is not that difficult. Come on. I know you can do it. Anyone would like to come up? So the base case and the recursive case is simple enough. Okay, we want to stop when the base case is like 0, or at reach the number of yeah. Okay. She doesn't like my name. Okay. Yay! Okay, test it out. Okay, as simple as that. Okay. So you actually work out with the in this case, the base case is hidden because when you hit the base case, you don't have to do anything. And the base case is when n equals 0. Okay? So you hide the base case because it doesn't require you to do anything. That's why you can hide it. Okay? So you just focus primarily on the recursive case, when the case where your n is not equal to 0. Okay? And once you get there, you start out with n. You start out by calling itself, but reduce the number of n by 1. Anyone would like to come up and trace this call, this method call? Use 3. What it looks like when you trace this recursive call. When things get expanded, when things get evaluated. It will be interesting in this case, really. Anyone would like to come to trace? Anyone? So based on this, you started out by calling print 3. Okay, you started out by calling print 3 downstairs. Okay, from print 3, what next? So this is your step number 1. Step 2 is what? Say again? No, don't worry about the condition. It's either expanding or evaluating. Yes, step number 2 is print 2. And step number 1 is print 1. I'm sorry, step 3, not 1. Step 3 is print 1. And then, is there a next step? Because now say n is now equal to 0. Okay? So when n is 0, you don't do anything. So really, step number 4 is evaluating. That is, I love Java. Alright? So you do I love Java 4, and then what? Another I love Java. Okay? And then 6, another I love Java. Alright? So you start printing it out at this point, followed by that 3 times. Okay? So the evaluation, the expansion and evaluation in this case goes from expand, and evaluate. Okay, that's the interesting thing about this example. In some example, you see a mix between expansion and evaluation. You expand and evaluate from time to time. All right? But in this example, you try to finish all the expansion first, and then all the way out or all the way up, depending on what you call it. You start doing evaluation along the way until everything is printed out. And that happened because of this statement. You're going to have to finish this one first until you reach the base case. And only when you reach the base case, you start going out with the print statement, one by one. So far, so good. Ready for another problem? Yes, you are, okay? So let's try this. You still remember what a palindrome is? Yes. You still remember what a palindrome is? Java, this is not a palindrome, okay? CSC, which is the course code, right? This is a palindrome, okay? This is a palindrome, okay? XOOX. This is not a palindrome, all right? So basically, a word is a palindrome if you can flip things up and then you get the same thing. Okay, so in this case, the cut line is here. You flip it up, you still have XOOX. In that case, you cut it right at the S. You don't flip the S because it's already exactly in the middle. So you flip C and C, you get the same thing. That is palindrome. Okay. What about this one? Is it a palindrome? Yes, this is a palindrome. Okay. All right, so we know what a palindrome is. I want you to write a method to check whether the word is a palindrome. So it should be a true or false. But I want you to do it recursively. So you want you to write a method maybe called each palindrome, and then you take a string as a parameter, solve it recursively. Check whether or not a string is palindrome recursively. So think about the base case when you want to stop, and think about the recursive case. And since you are working with the string, you might need to take a look at the Java documentation on the string class. What methods are available that you could use? In case you want to know how you want to spell a palindrome, okay. And don't be shy, you can talk among yourself, okay? Just try to brainstorm and see if you can come up with the solution. Are we almost ready? Which group already finished it? Mountain path, you done? Almost? Okay, we're gonna wait for the mountain path, okay? Okay, so your friends are ready. Are you gonna send your girls to do the solution? Well, lady first, right? You're gonna give the well. They should have the honor, ladies. So one type, one explain maybe. And the microphone is all yours. So typing and
สปีกโนโดเหม็นนั่งลุกเลย
ไปทำไมต้องเป็นบุหรี่เอาบุหรี่
Let's explain what your approach, what's the best case when you are checking for the palindrome stops, okay? And how you inch closer and closer to the solution.
อะไรพูดดิพูดเลย
มึงยังพิมพ์ไม่เสร็จอ่ะ
Try to be nice and put that. Let's just put a quote here.
ช่วยกันก็no this method hello like you have to like put the string and then the I forms zero is like start from the letter zero and the first line if the first if we go is used for check like if it's true or not like over here we should like if it length like just one letter that means it's two right and then this when we check we check to like to the middle of the word here and then it true yes and but when we gonna check this word we like I is I is zero yeah
we just keep recursive it if the I greater than the length divided by 2 yeah it will return 2 that's it if it not it will fall yeah the fall we check if the we check first I begin with yeah and if I
yeah and then
and if the I
like palindrome is this letter have to equal with this letter right and then it's keep like equal yeah and then we should to check like first one to the last one and then going next and next like yeah if it not equal it's going to return false but if it equal it will not going in this if and it will return like recursive call and call again to check like to the next letter.
it will return false for this word
Yeah. Thank you.
You know, when you test, you should try more than just one case, okay? Like, for example, you have the correct one and then you expect the false. Okay, try them all, not just one, to make sure that, you actually fit all the cases there, okay? But I believe most of you, when you actually work on this, your approach seems to be similar. Okay, so if you have a string, what you actually do is that to check for a palindrome, you started out with the first character against the last character, right? And then if they're right, you move on to the next. If they're still okay, you move on to the next one. You keep on doing this, okay? But as soon as you find a pair that is not correct, you should stop, just return false. By returning false, that one, you won't go any further to the recursion because now you return a false and everything will be a false, okay? But that's the theme that most of you would do. Now, with this theme, what is the best case? What is the best case here? The base case equals 1. What is equals 1? String length equals 1. So that meant what? Is it ever equals to 1? This line right here? I'm just curious. Is this ever become 1? String dot length right here. I know that this is, it is true when you actually reach the string dot length divided by 2. But you use an or, not an and. So if that is true, this never be true, you still get a true. The question for you guys is this ever true? Ever false, I'm sorry. Or true, I'm sorry. Is this ever true? Yes? No, never true. It's always 5. This is 4. So what you need it is you don't work with 1. I mean, you are using that because you want to deal with the one word case, is that it? Okay. So when you move beyond the halfway point, and if the string length is just 1, you will return true right away. Okay, fine. Okay, gotcha. Okay. Anyone else use any other approach? Let's do another one, just for a kick. So the best case right here is that we're going to move. The recursive will be the shift of the string here from that to this to this. Okay. So whenever your string is 1, or whenever your string is 1, that means you are reaching the base case. And when that is the case, you always return a true. Okay. So we're going to do s.length less than or equals 1 when that is the case, which is the base case right here. Well, we just return true. That's unconditional, right? That's true. Else if. Okay, note that we are using the if and else if to make sure that we string everything together. Try to avoid using if and if and if because you are going to execute them every single time. Here also is another base case, but this time you return false. Else, the last one you just recurse, okay? And you use a substring. Substring, yeah, small s. From 1 to s dot length minus 1. Okay. S E N G. Okay, so we have what? Oh, wrong one. Okay, so that's another approach if you want to try it. Okay. But this one is kind of clean in a sense that you are pretty explicit on what you want as a base case. The first one as a base case is when you reach the middle right here. Okay, so every time you call the method itself, you send a substring instead of the string. Okay, so from the full string, the next time you call it, you're going to remove the first and the last character, and then you send in the substring right here, and then you send in another substring until you send in only the last character. When you reach the last character, then that is your base case. Okay? When you have the last character, it will always be true. Otherwise, to check each of the character in the first and the last. Okay? This one you check the first and the last character. If the first and the last character is not the same, you don't need to go further, you stop. Because that is always going to be a false. But if they are the same, that falls into this category. If they are the same, you remove the first and last character and send a substring in there and check the substring if you reach the base cases here. Okay? So this is what this approach does. All right, any question on this? Recursion is fun, okay? And it requires you to do some recursive thinking in order to get this right. It is not difficult, it is not overly complicated. All you need to be aware of is that it always has the structure that you should be following. You should look for the base case, okay? Or the base cases. You should always look for the recursive case where it must reduce itself toward the base case. Because if it cannot reduce itself toward the base case, what's going to happen? It will blow up. All right? It will explode. You won't be able to get the recursion to stop. All right? So that's the whole concept of recursion. Okay? So time is up pretty much. And don't forget about Monday and Tuesday. Okay, we have the appointment on both days. Okay, so good luck to you all, and I'll do the announcement to confirm the date, the time, the date, and the date is already confirmed. Okay, Monday and Tuesday. I just want to confirm the time, the place. For now, on Mondays, we're meeting in the training rooms. It's not for now, it is. Okay, on Monday, we're meeting at the training rooms. Okay, and I'll do an announcement why exactly. Right now, we do 1 and 3. Actually, we do 1, 2, and 3. Okay, But for Tuesday, right now I make the reservation on for the training room, but my wish I want to go upstairs to the fourth floor because that's bigger and it's easier for us to do the demo, the presentation. Okay, but I will confirm if we're going to move up to the fourth floor of SIT building, and then we use the big room to do the demonstration. All right, thank you very much. I'll see you next week.